Very good morning, all. Let us better understand generators. And of course, three key topics which we have given. There are three topics which we have promised. One is capability curve of the generators. Second one, mode of AVR modes of operations, governor modes of operations. These are the three key important aspects which we have talked about. Let's start with the capability curve. Why we are talking about the capability curve of only the generator? Why not a transformer? Why not a motor? Why not a cable? Why not a transmission line? Why the terminology capability curve is stressed for generators, not really for a transformers or transmission lines or a cables or a motors? Generator also has its rating. Motor also has its rating. Transmission line has a rating. Transformer has a rating. Why capability curve only for generators and of course maybe inverters in case of solar inverters? Why not for other equipments, motors, transformers, transmission lines, cables, etc.? Why only one rating which is enough, good enough for a transformer or a transmission line or a cable, but that's not really sufficient for a generator? Let me ask this question, like generators are rated in, because like we say, like transformers are rated in, correct? No, transformers are rated in VA or KVA or MVA. What about the generators? Generators, it's a bit tricky. If I am saying 500 MVA for a transformer and 500 MVA for a generator, it is not really communicating the same message. Though the transformer is a device which just change the voltage and sending the power from one side to the other side, and the generator is generating power, it is also logically means what say converting a mechanical energy to the electrical energy. So it's kind of the same thing, but like there is a big difference, and that big difference comes from its independent real and reactive power capability. What I mean when I say 500 MVA for a transformer, whatever may be the real and reactive power combination can be used. Means this, whatever may be the combination of P and Q, which can flow through the transformer, which makes the transformer MVA rating 500 MVA. Whereas the generator has independent real power constraint, independent reactive power constraint. What I mean by that, let's have probably a paint. So I have kept x-axis and y-axis. First, let me take a transformer. Let me try to draw capability curve of the transformer. Transformer has a capability curve. Unfortunately, like we are not really worrying about it, but like literally, like it has a capability curve. The capability curve of the transformer is a circle, and its center is 0, and its radius is its rating. So if you are keeping whatever may be the power which you want, say example real power in x-axis and reactive power in y-axis, if you are keeping transformer capability curve at least theoretically a circle, right? What it mean when I have a, when I'm saying like 500 MVA is a transformer rating, the transformer can be loaded with whatever may be the combination of P and Q, which makes the total apparent power 500 MVA. We are talking about a transformer. We told transformer is rated in VA or KVA or in MVA. Like literally we have taken a 500 MVA transformer, maybe 400 bar 220 kV ICT, interconnecting transformer. And we are asking about what's the P value maximum this transformer can allow to flow through, what's the reactive power. There is no independent real power constraint. This can be any number. The S apparent power, of course we are very much aware what is P, that is real power in megawatt or kilowatt. Q, we are very much again aware it's reactive power, and like we are aware it's apparent power as well. So there is no independent control on P and Q. Only constraint is an apparent power, which is to be 500. That's all. That's pretty much it. Which means you can probably have multiple P and Q combinations. What I mean, you can have 500 megawatt with 0 MVR. You can have a 0 megawatt with 500 MVR. You can have 400 megawatt 300 MVR. You can have 300 megawatt 400 MVR, or whatever may be the combination. You might be aware the power triangle. Apparent power S is square root of P square plus Q square. So square root of P square plus Q square, whatever the value which you keep, as long as it meets the apparent power of 500, it's good to go. So there is like all the cases, whether it is 500 megawatt 0 MVR or 0 megawatt 500 MVR or a 400 megawatt 300 MVR or a 300 megawatt 400 MVR, like apparent power remains same, and you do not have a constraints the transformer capable of handling this power. So I have given few combinations. You can probably fill up whatever may be the combinations. Square root of P square plus Q square. If it is equal to 500, your transformer is capable of handling that power. So this is with respect to the transformer. But what about generator? Generator also I'm saying say 500 MVA. Typically, you may not see the generators as 500 MVA, right? You might have here the generators like 500 kVA with the diesel generators, but like when it is higher capacity, you always deal it in megawatt, right? How many of you have here 500 megawatt generators? Let's have this combination for a generator 500 MVA and ask the same question: is it technically possible for this generator? Technically, both of this is not really a, I mean, for say operating point, or the generator is, though we claim that it's a 500 MVA, it may not be able to generate 500 megawatt, or it may not be able to generate 500 MVAR. Similarly, this combination is also difficult or impossible, right? Only combination which might be possible is this one. That means you can go up to maximum 400 megawatt and you can go up to maximum 300 MVR. That is also probably dictated by some other parameters. That is, what's the power factor of generator? If the generator power factor is, say, example 0.8, if the power factor is 0.8, then this 400 megawatt 300 MVR combination is a technically an operating point. But if the power factor of this generator of 500 MVA is, power factor is, say, example 0.85, if the power factor is 0.85, then 400 megawatt could be the operating power factor, means for say operating point, but definitely 300 MVR cannot be the operating point. And I guess like that's all I want to convey with respect to, I mean, for say this capability curve to understand. So coming back to this capability curve of the transformer, capability curve of the transformer is a circle, and its radius is equal to its rating in kVA or MVA. You can load this transformer fully by real power. This point is like 500 megawatt, right? 500 megawatt 0 MVR, which is technically possible. This is like, this operating point is like 0 megawatt 500 MVR. Here it is like minus 500 megawatt, reverse direction. Also, transformer is a bidirectional device. The power can flow in the reverse direction. 0 MVR, that's pretty much possible. 500 minus 500 megawatt, this is 0 megawatt minus 500 MVR. So all this combinations are possible. And in addition to that, probably say example, if you're picking a point somewhere here, this point. So this point is something like this. Your P is something maybe 400 megawatt. Your Q might be 300 MVR. This combination is also probably possible. So as I told, means what, say you can go, means what say, obviously you can go inside the circle at any place, and you can probably, means what say, go up to the maximum operating point of anywhere in the circle outer line also. So P do not have an independent constraint, Q do not have an independent constraint. But I cannot probably apply the same rule for a generator. Means transformer, like it's a circle, it's a bidirectional, all these things. But when it comes to the generator, generator is a source. So generator power cannot go to negative. So straight away, half of the portion is eliminated. So means what say here, and this portion is technically not possible to operate because generator will trip in a reverse power, or even in fact a low forward power. Even before reverse power, there are generators which will trip on low forward power. So technically there is something called technical P minimum of the generators. The generator will not be able to operate below certain real power capability. That's a constraint, right? So if you want, probably we can check or test that in ETAP 2. Like I'm just picking a generator here, and maybe let's look at fuel cost. There is something called minimum megawatt and maximum megawatt. If we say 500 megawatt generator or 400 megawatt generator, it doesn't mean the generator can operate anywhere between 0 megawatt to 400 megawatt or 0 megawatt to 500 megawatt. Answer is no. There is something called technical P minimum. Can you say like what's the typical technical P minimum value for thermal generators? So technical P minimum is dictated by the generator, dictated by the mechanical constraints of turbine, vibrations, maybe white smoke in case of diesel generator, etc. Typically, it will be in the range of about 25% to 30% for diesel generators. It could be anywhere between 20 to 30% for thermal power plants. Of course, it's not a momentary, it's a continuous power. So what I mean, if I have a 500 megawatt generator, I cannot run consistently at 50 megawatt for like infinite time. So as I told, like diesel generator, white smoke will come. So it reduces the life drastically. Thermal generators, you will be having a mechanical vibrations when you are operating at like much lower power. Let's go to the again capability curve. So if I am picking up a capability curve, keeping again P in x-axis, Q and y-axis. If it is a generator, generator cannot have the operating point in the negative P, right? This is negative P. So here it's obviously ruled out, like means for say here there is no way the generator can operate because generator cannot consume power. If generator consumes power, this becomes a motor. If generator starts consuming power, it is no longer a generator, it's a motor. It's not practically possible for a generator to consume power. So it's not going to be operating point. And of course, few textbooks or few illustrations keep P in the y-axis and Q in the x-axis, which you can try whatever may be the combination, just like rotating the capability curve. I am not really worried much about it. Now, at least talking about with the same thing, okay, like still I'm trying to draw a circle, treat it as a circle. Like because of the negative power, the side combination is ruled out. Let that be fine. Like this is not operating point. That's pretty much clear. That's what is the dark color, which is not operating point for a generator. If we want, like we name it as a generator. So means we say the semicircle on the right hand side with a positive P. Is it possible technically? That is also not technically possible. That's the reason why the capability curve takes really an important aspect with respect to the generator. So if you take a generator, like as I told, what you need to put another line is P minimum, technical P min. You cannot go below this, and you will be having many other constraints, right? Like who is probably putting a cap on the P is P max. That P max is dictated by the turbine capability. If I have 500 MVA generator, that's literally a 400 megawatt with 0.8 power factor generator. So you will not means for say design 500 megawatt turbine, you will design only 400 megawatt turbine. So the Pmax value is limited by the turbine capability or the input capability, whatever it is. Valve wide open condition of your thermal power plants, like you can take any other types as well. So if you take thermal power plant, valve wide open condition of the turbine decides what's the maximum real power this generator can generate, beyond which it cannot generate because the input is not available. So means what to say now, means what to say, I'm just trying to probably put the dark color wherever it's not practically possible. This is ruled out because your generator is not capable of generating because the turbine is not giving that much input power. Only when turbine gives the input power, generator can generate that. So below this also you cannot generate. That's because means for say mechanical vibrations or means for say smoke, white smoke in case of diesel generators, etc. So what are the other constraints which can probably come? There is something called stability limit when you are consuming reactive power. When the thermal generators are consuming reactive power, there are two things which can happen. One, end ring heating, and probably the stability constraints. Both the constraints can come together. And when you're generating higher reactive power, like means to say when I probably reduce the P to 0 or like 20% or whatever it is, and shall I generate remaining as reactive power, that's also not possible. That's dictated by your rotor heating limits. So now probably means to say the capability curve of the circle of a transformer, like we have deleted left hand because the power cannot be consumed by the generator, and we have added a P minimum, that is below which the generator will go to the vibration or it will generate white smoke, etc. And we have removed that portion, and we put a P max, and above which it cannot generate because turbine cannot capable of generating it. And then probably means what say on the reactive power consumption side, we have told two different constraints. One constraint is end ring heatings, and other one is the stability constraints. Two constraints which we have had. And of course, on the reactive power generation side, you have a constraint of rotor heating, right? And if you want, you can probably write this is rotor means turbine limits. Here it is stability limits. Here it's vibration for thermal or a white smoke. Probably like previously what you have seen, you have seen a circle where you can play at any place as an operating point in your transformer, but that's not so the case for your generators. What's the purpose of AVR? Let's come to here, right? It's a bit tricky here to talk about. So, means what say, if you have automatic voltage regulator AVR, that's basically an electronic device called electronic device, right? Like it's kind of a control device, kind of a relay, or you can call it as even IED. That's absolutely fine. So AVR is not an excitation system, not really to confuse. AVR is something different. You have an AVR for a transformer also. Where AVR is used in transformer? If you know the answer, can you just put it? AVR is available for generator, AVR is available for transformer also. Where AVR is used in transformer? Give a control to the unload tap changer. Unload tap changer is provided on the high voltage side of the transformer to regulate the voltage on the low voltage side. But when to change, how many steps to change, how much time I have to wait, all these things are basically dictated by the AVR. That is also an AVR, right? Automatic voltage regulator. But there is a difference between AVR for a transformer and AVR for a generator. There AVR is discrete, like I will be having 17 taps or 9 taps or 5 taps. So when I'm changing the voltage, I'm controlling the voltage there also with the definite time delay, and the time delay is controllable in AVR. And when I'm changing the step, it is probably changing 1.25% voltage or 2.5% voltage. But when it comes to the AVR for generator, AVR is not really changing some step or something. How AVR in generator regulates the voltage? So there is always a generator, and the generator is connected with the VT. So the voltage at the LV side of the VT is measured, monitored, compared against a reference value. Whenever there is a reduction in voltage, your AVR will send a command to the excitation system to increase the field voltage and hence increase the field current, and hence the generator will generate more reactive power and this terminal voltage will boost. I guess like electrical energy systems and controls by Elgart probably talk about this PF loop and QV loop in a much better way. Electrical energy systems theory and introduction, and like they talk about PF loop and QV loop, and if you are in India, you can probably put it in even Amazon also. It's not so expensive, right? Amazing book to go through, and that gives like what is the reactive power, voltage and reactive power, right? Let's get some AVR loop in generator. Let's see whether we are getting some good images. Yeah, of course, generator, voltage sensor, automatic voltage regulator, excitation system, generator field. Generator field is basically a rotor, right? So here the voltage sensor obviously has like voltage transformer, and then probably that passes this information to AVR. So this AVR not necessarily has to operate only in a voltage control mode. It can operate it in any mode. It can operate it in voltage control mode. It can operate it in MVR control mode. It can operate it in power factor control mode also. Voltage control is what like we are already aware of, like quite frequently what we are doing of. But MVR control, what it will do, irrespective of whatever maybe the real power the generator generates, irrespective of whatever the real power the generator generates, reactive power is fixed. So that's MVR control. Then what's the difference between MVR control and power factor control? There is no difference between MVR control and power factor control if real power generation remains constant. Say example, going back to this Excel, if 400 megawatt 300 MVR, I'm putting this generator in MVR control mode with the 300 MVR, or I'm putting the power factor control mode and putting the generator in 0.8 power factor. Means what, say 400 megawatt 0.8 power factor corresponds to 300 MVR. So means what, say as long as the generator is generating 400 megawatt, the generator will be keep generating 300 MVR. That's the reason why I told MVR control mode and power factor control mode remains same when the real power remains constant. When the real power has changed from 400 to 200 megawatt, like that means if it changes from 200 megawatt, 400 megawatt to 200 megawatt, if I am putting that in MVR control mode, this will tend to generate 300 MVR. That's in MVR control mode. If it is in MVR control mode, if it is in power factor control mode, this 200 megawatt, it will generate only 160 MVR. MVR control and power factor control are one and the same when the real power is fixed. Because when you have fixed real power, if you fix MVR, then obviously power factor is fixed. When real power is constant, when the power factor is known, MVR is fixed. So when real power remains constant, MVR control mode and power factor control mode are not really too different. But when the real power is consistently changing, then you have a different meaning of MVR control and power factor control. Irrespective of whatever the change in the real power, reactive power is maintained at 300 MVR. That is MVR control mode. So when power factor is set to be 0.8, when the real power is changing, reactive power is adjusted to maintain the power factor as a constant, which is 0.8. That's the power factor control. Q equal to V square by XC, V square by X, in fact. So that Q is proportional to square of the voltage is applicable for passive LC, inductance and capacitive equipments, not really for generators. So we have seen what is voltage control, what is MVR control, what is power factor control. And let's ask, this is AVR mode, then like what is governor mode? Governor can probably operate it in two different modes. One, constant frequency mode or constant power mode, and over and above this can probably operate it in a droop mode also. Governor can operate it in constant power mode. Typically cogeneration plant generators want them to operate it in constant power mode, there is something called constant frequency. What's the beautiful name which we generally use for a constant frequency? There is a beautiful name which is available, which is might be very familiar for everyone. What's the name of, what's another important name which we generally use for a constant frequency mode? Isochronous mode. Constant frequency is also called as isochronous. What does it mean? When to put this generator in isochronous is also really important, right? I mean, for say you cannot really put a 500 megawatt generator which is operating in with the grid, along with the grid in isochronous mode, right? Whenever there is a change in frequency, this generator will adjust its real power generations, bring back this frequency to the rated frequency. That's isochronous mode. Where this constant frequency or isochronous mode is used? Only when you have one generator. Let me repeat my statement. When we have only one generator which is feeding the loads, by the time that generator has to be in isochronous mode or a constant frequency mode. If you have like a very grid connected operations, then like you will neither operate in constant power nor operate it in constant frequency. You will go for something else called a droop mode. So all grid connected generators will operate it in droop mode. If you have only one generator, like a diesel generator operates just to feed the loads, then you will operate it in isochronous. You're not connected with the grid, but still you have like multiple generators, not one generator, 3 generators or 4 generators you have. Then what mode you will operate? Like we have discussed, like only when you have only one generator, you have to operate it in constant frequency. If you're connected to the grid, you have to operate it in droop. But like I am giving a third scenario where it's a standalone system, it is not connected with the grid, but it is not only one generator. I have 2 generators, or I have 3 generators, I have 4 generators. What mode it will operate? So they will operate in isochronous, but isochronous load sharing. I guess this you will face only in a standalone systems with a few generators, right? Especially when you are working with like FPSO projects, offshore projects, like 3 gas turbines, 4 gas turbines, maybe remote mines. You will be operating with like 7, 8 diesel generators. You will be needing it, and probably as a system study engineer, you will be having more challenge there in balancing real and reactive power sharing equally across all generators, even during sudden changes, right? It's important. You need to like say why here like one in ISO and remaining generators in droop may not really work out, is because that ISO generator will be taking like whatever may be the sudden mismatch. That might be the real reason why like this is not recommended, and you have to go with an isochronous load sharing. Whenever there is a change, the change, increase in demand or a decrease in demand, has to be distributed across all the generators proportionate to their capacity. That's basically an isochronous load sharing. So then we can ask why ETAP has not really given this here. So here swing mode is probably, swing and voltage control are probably bit overlapping statements. When your generator is operating in V by F mode, that means constant voltage, constant frequency mode, then that is called as a swing. Constant voltage, constant frequency. Here voltage control means that's applicable only for AVR. MVR control, it is applicable only for AVR. Power factor control, it's applicable only for AVR. But swing is basically, it's about frequency, it's basically about real power. And like they have given our operation mode, but like since ETAP performs the load flow with slack bus concept or a swing bus concept, where the mismatch between the generation and demand is compensated by the slack bus itself, which means it's not reflected as a change in frequency. They have given as a swing, but literally, I mean, so to say, there is something called, I'm not really sure how many of you are aware, there is something called frequency dependent load flow. If you know what is frequency dependent load flow, just type FDLF in chat. There is something called frequency dependent load flow. In reality, whenever like load flow, you may not use the terminology frequency at all, but in reality, like if you go to means what's the real time and measure the frequency will be keep changing. Why the frequency is changing? Whenever there is some mismatch between the generation and demand, that's reflected as a change in frequency, right? Unfortunately, your load flow will not be able to capture this if we are not using FDLF. Like predominantly 99.9% of the cases, softwares are using swing bus or a slack bus concept load flow, which cannot capture what's the change in frequency. Thank you all. Thank you. Have a great day.